So welcome, you're here for an exciting day, as today we are going where no man in this course has gone before, and we are going to be trying to factor this matrix here, yes, this matrix, into three different, very important matrices. So fasten your seatbelts, we're here for a wild ride with diagonalization. So for diagonalization, we are going to call upon our good friends, our eigenvalues and our eigenvectors. We are pros by now at solving for eigenvalues and eigenvectors, so I'll just tell you what they are. Our first eigenvalue is -3, our second eigenvalue is 3, and our third eigenvalue is 1. Our first eigenvector corresponding to our eigenvalue of -3 is going to be -1, -3, and 2. Our second eigenvector corresponding to our eigenvalue of 3 is going to be our simple 1, 0, 1. And then lastly, our third eigenvector here is corresponding to our eigenvalue of 1 is going to be equal to -3, 1, 0. Okay, so to factor this matrix A, we're going to first see what we can do with our eigenvalues, eigenvectors, and A. So if we take A here, we're just going to copy it down. We have 1, -1, 3 as our first column, 0, -2, 3, and then 2, 1, 2. And we are going to take this matrix, and if we were to multiply it by one of our eigenvectors, let's just take our first one here, -1, 3, and 2, what would we expect to get out? So multiply this out here. We would expect on this side to get -3 times v1 as our first column here. Okay, wait a second. How did we get that? Because that's the definition of our eigenvector. When we multiply it by this matrix A, we are going to get lambda times that vector. So we know when we multiply this row by this column, we're going to get this one out here. Okay, and then we're going to do the similar thing. We have our second eigenvector here, and then our third one, we can expect to get 3 times our second eigenvector here as our second column, and then 1 times our third eigenvector here as our third column. Okay, so we have some pretty cool stuff going on here. But I said we were going to factor into 3 parts. So right now we have A, which is what we're factoring, so we're not going to worry about that right now. We're going to call this matrix here P, and that is the matrix with all of our eigenvectors as our columns here. So we're going to want to make sure that we have n linearly independent eigenvectors that we can plug into here. And then on this side here, we are going to try and break this into now 2 pieces. So how can we do that? Let's go ahead first and copy down A and P. Okay, so before we get into this, let's kind of like look over here and let's just try something out. So if we were to take some matrix A, B, C, D and multiply it by, let's say, lambda smiley face, 0, 0, and lambda frowny face. When we take this product, what are we going to end up with? Well, this is going to equal A times lambda smiley face. So you have A lambda smiley face times, or plus, C times 0. So we're just going to have that. And then if we go first row, second column, we're going to have A times 0 and C times lambda frowny face. So we're going to have C lambda frowny face. And then we're going to have for our second row times our first column, B times lambda smiley face times D, or plus D times 0. And then we're going to once again go second row, second column, B times 0 plus D times lambda frowny face. So if we notice here that all of our lambdas with the smiley face are in our first column, and they're in the first column of our matrix here. So let's try that out. So if we take our matrix here, and let's just rewrite P, because we know that that is the matrix of all of our eigenvectors. We just copied our p down over here, but we know that that is not equal to what we have equal on this side. So, what can we do? Using this logic here, so keep this in mind, knowing that when we multiply a matrix on the left by something that kind of looks like our identity, whatever is in that column of our identity type matrix is going to be multiplying everything in the corresponding column of the matrix you're multiplying on the left by. So let's try that. So we know that we want in our first column here, we want to multiply everything in our first column, which is our first eigenvector, by our first eigenvalue. So let's just plug our -3 in there. We're going to have zeros everywhere else. And then we're going to, for our second eigenvector here, we know we're going to want it to be 3 times this one. So we're going to put our 3 in there for, it's in our second space here because it's going to go for the second column here. Okay, and then lastly, we're going to see our third vector, eigenvector, has an eigenvalue of 1, and we're going to put that in the third row right here. So now you can check this on your own to see that truly, really, truly, tried and true, this times this matrix, so our P matrix times this matrix with our eigenvalues on the diagonal is going to give us our A times P. So using the definition of eigenvector, you can verify that this is true. So we see that this is P, and then we're going to call this D because we have our eigenvalues on the diagonal. Okay, so wow, we just came up with one of our super cool star equations. We're going to call this star equation 1. So we have found that AP equals PD. So I promised you that we were going to factor A into 3 parts. So how can we do that? We can multiply. We have our AP equals PD. So if we multiply here by P inverse on the right, we'll end up with A equals P times D times P inverse. And this is our second star equation. And then lastly, we can go the other direction too and show that D is equal to P inverse times A times P. And that is our third star equation. So these are going to be super helpful for us and just kind of describing the matrix A in a different ways. So we have to find our eigenvalues and our eigenvectors in order to get to this point. So it seems kind of circular. But if we wanted to calculate a power of A, this second equation here is going to help us so much. So let's just look at if you want to take A squared. If we had to do all the matrix multiplication of that, that might take us a little while. But luckily, we already know what A is equal to. We know A is equal to P times D times P inverse. So if we square this one, we know that A squared is equal to this. And then we see here in the middle that because matrix multiplication is associative, that these two are going to cancel out into the identity. So we're going to be left with A squared is equal to P times D times D, so D squared, times P inverse. So now let's think, okay, how hard is it to compute D squared? If we look at what our D is right here, this is our D. To square it, all we have to do is square each term on the diagonal. So simple. So we know how quickly and easily we can find our A squared using our P and our P inverse and our new diagonal. Diagonalization is also a really cool way to show off your mad math skills to friends and kind of blow their mind with just how groovy math is. So you can take a bet, be like, hey, I bet I can factor this random matrix into 3 parts. But first you want to make sure you probably have n linearly independent eigenvectors first. But enjoy being able to use diagonalization and go have fun make good choices, diagonalize hard. Have a great day.